Sit down. Please.
All right. You'll just, I assume, come back in if you still can't hear anything. All right. Right, so thank you all for coming today to listen to me speak about my ongoing research on optimizing quantum transport. I've been working on this for a little over a year now, so I'm hoping to kind of wrap things up soon. So I have some neat results to show you. But to start, just so that everybody has the same level of knowledge, I'm going to just explain a little what quantum transport is. So I'm defining quantum transport, as do most people, I think, as the transfer of energy excitations between coupled quantum sites. Oh, we should close this thing. Sorry about that. There. So quantum transport occurs in quantum devices like quantum computers, also in solar cells. There's also some plants, specifically some bacteria, where their photosynthesis complexes follow a procedure that we think is quantum transport. So overall, we see it all over the place at the quantum level in the world. Oh no, now I think it's because I closed that thing. All right, just let me, great. So my goal with my current research is to design quantum systems to maximize this quantum transport, which would be a relevant question in fields where we might want to design something like, say, a solar cell or some sort of quantum dot-based quantum device. So I'm optimizing quantum transport because that is the most relevant quantity to calculate for experiments or simulations or devices where you're interested in energy transfer or exciton transfer. But there are other quantities that I could have also used that would be also easily optimized with the same procedures I'm about to explain, like dephasing rates or charge transfer or heat transfer. Anything that can be measured in real experiments in theory, this would apply with too, but I'm choosing quantum transport. So a little background on open quantum systems, if maybe you're unfamiliar. An open quantum system is just a quantum system that can interact with its environment. So typically in your quantum mechanics classes, you'll kind of learn about closed quantum systems where everything evolves according to the Schrodinger equation. You get nice Rabi oscillations. Here I'm including an environment. So I'm considering the whole system and environment or bath to be a closed system, but my system does interact with the bath through some interaction Hamiltonian that I assume is weak and that factors into a system part and a bath part. Also for the system, by the way, I'm going to use the tight binding Hamiltonian throughout this whole talk. So that just means that I'm limiting myself to a single exciton in my system at one time. All right, I'm going to simulate these open system dynamics with the Lindblad-Master equation. So the general form of the Lindblad-Master equation is there's two terms to it. The first is the unitary term, which you can get that term from the Schrodinger equation that describes the unitary evolution of the system due to its Hamiltonian. Then there's also a dissipative part that describes the effects of the interaction with the environment or the bath on the system dynamics. So including the dissipative part will dampen those Rabi oscillations I just mentioned until you reach some flat steady state. And to obtain this steady state solution, you would solve this Lindblad-Master equation for the time derivative rho dot of the system equal to 0, which is what I'm doing for my own calculations. So my figure of merit that I'm trying to maximize here specifically is the quantum transport efficiency. So first of all, what I just mentioned about the environment causing dissipations in your oscillations, and then you reach some flat steady state. Using an infinite temperature environment, which I am doing for now, just for simplicity, that leads to just every site having an equal probability of the exciton being there, which is kind of boring. So I am imposing a current kind of through my system, where I allow excitations to leak out of the last site in my chain, and then I re-inject that energy into the first site so that there's a constant flow. So there's still a steady state solution that exists for this system, and that steady state solution depends on the rate of extraction and injection into the system. So the transport efficiency definition that I'm maximizing is here. Eta is the Greek letter I'm using to denote transport efficiency, is equal to this leakage rate multiplied by the steady state density matrix population of the final site in my system. So it's kind of like calculating the flux through that last site. And I use the Lindblad master equation that we just saw to calculate that steady state density matrix. So my research is a little unique in that I'm actually optimizing the system energies, which doesn't get done very often. Typically, you would see someone wants to study how a particular system behaves given different environments, and then they change the environment, and then we discover things such as environmental noise-assisted quantum transport or localization or other things. However, I instead am going to fix an environment, and also just to limit my number of free parameters, I'm also fixing inner site couplings, and I'm allowing the on-site energies of my one-dimensional chain to be my free parameters that I change with the optimization. So this would be relevant, again, for systems where you might want, or for projects where you might want to design a system, again, like some sort of quantum wire or solar cell, rather than when you already have some sort of system and you want to find an environment for it. So last little bit of background before I go into some results. Sorry, this white is not showing up very well. Yeah, anyway, so I'm using gradient ascent to do my optimization. Gradient descent is an algorithm that's often used to tune neural networks, and it's possibly the most intuitive optimization algorithm I've ever used, where I just, at a certain point in my parameter space, which in this case is some hypersphere of n-1 dimensions with all the energies, and then I calculate the gradient in every direction, and then I step uphill, and then I try to keep going until I reach the maximum. So very simple to implement, it's quick, and there are a few caveats to think about. For example, my stopping condition is just when my gradients are sufficiently close to zero. Obviously, with computers, you never get exactly zero, but in that case, I also say would stop the algorithm if I found a saddle point, which I don't want. So I do have to take that into consideration. But generally, it works very well. And you would typically hear of a cost function with gradient descent, or in general with optimization. I'm just maximizing my transport efficiency. So again, this eta equals gamma leak times steady state density matrix elements, and I get that density matrix element using the Lindblad master equation. All right. So now into some results. I started by doing a lot of simulations just with 3 site systems, because in this case, I only have 2 free parameters, because it's only the energy differences that go into what affects the behavior of your quantum system. So this way, with only 2 free parameters, I can make contour plots to look at efficiency, and then compare where the contour plots are showing me maxima to where my optimization algorithm is converging to. So the simplest case I can show you right now is just a 3-site system with nearest neighbor coupling, but not next nearest neighbor. So sites 1 and 2 are coupled, sites 2 and 3 are coupled. And the optimal solution in that case is just a flat profile. And I looked into these numbers, and they are all like 10 to the minus 5, 10 to the minus 6, which would be roughly within like the floating point error tolerance of my simulations. So they are essentially 0 here. Again, keep in mind that I'm doing this at infinite temperature. So it is just as easy to go uphill as it would be to go downhill. So if you were expecting, well, why isn't there a downward slope? That's why. So not too much interesting going on here. However, when I include coupling between the first site and the third site, so now I have like all-to-all coupling, I get two solutions and a much more interesting contour plot. It's maybe not too obvious like on the screen with the contrast issues, but there's like an optimum ridge along here where the efficiencies are all kind of the same. So the way I'm interpreting these results is that when you can have your exciton go directly from site 1 to site 3, the optimal solutions are the solutions that get site 2 just out of the way. And then instead of going site 1 to 2 to 3, you can just bypass 2. So that's what this ridge is showing. Sites 1 and 3 are roughly at the same level, which makes sense because we want our exciton to go from site 3, leak out, and then back into site 1. But site 2 can kind of be anything along here except near 0, which is a saddle point, which again, then your exciton would jump 1 to 2 to 3 instead of just 1 to 3. So here I have these two solutions that I hope the colors are obvious enough. So my first site is at energy level 0 in both cases. Then this orange solution, which is over here on the left, is one where you have a shallow V model. So site 2 is lower than site 1 and 3. And then over here on the right, the green solution, this one is more of a lambda model. And site 2 is all the way up there, far away from sites 1 and 3. And again, we're explaining this as just the exciton wants to jump from site 1 to site 3 and bypass 2 altogether. How am I doing? Oh, I still have 10 minutes. Okay, we might have more time for questions. Right, so once I was confident that my site or my 3-site optimizations were going well, I moved on to larger systems, which I can't really visualize nicely in 2D. I've tried we have successfully done some clustering and embedding and whatnot so that we can kind of visualize them in 2D, but it's just easier to look at the energy level diagrams here. So I looked at two schemes, long-range coupling and short-range coupling between the sites. So here I'm using power law coupling. So this would be, on the left is actually some J max over separation to the power of 1. On the right is some like max coupling over distance to the power of 3, which would be like your dipole coupling, say. So with this long-range coupling, we see something that's kind of analogous to what we just saw, where sites 1 and site 10, so the first site and the last site, are near each other in energy, which we expect because we want the exciton to just leak out of the last site and go back to the first site. I think all these intermediate sites are just kind of trying to get out of the way, is the best way we can explain it. So obviously, there's going to be some jumping through all the sites, but in theory, it's easier to just go from site 1 to site 10, is what we think. We haven't fully wrapped our minds around these results yet, but that's our current working theory. Then on the right, that's the short range coupling. So notice that the energy scales on the y-axis here are very different. Here I have from 0 to -2, and over here it's 0 to -0.1. So again, all the energies are relatively similar to each other so that your exciton can just pass through all of them. Right, we don't have great explanations beyond that for why these results look like that. At the end, if I have time, which I probably will have time, I can show you those actual values if you're interested. Right, so this is what I've done so far successfully. I've done lots of other things too. But my next step, which I'm working on now, but my results weren't ready for today, is to reproduce these optimizations in finite temperature environments. So right now with infinite temperature, if you can get kind of infinite energy, not that you're getting energy from the bath, but if you have like an infinite temperature bath, it doesn't make a difference to you whether you go uphill or downhill. However, with finite temperature, then you get some statistical mechanics like the Bose-Einstein distribution comes in to start dictating your transition rates between sites. So there we expect to see it's easier to go downhill than uphill. Also, I want to examine the effects of allowing multiple excitons to exist in my system. So currently I mentioned I'm using the tight binding Hamiltonian, which limits me to one exciton in my system, which in a lot of situations, like the photosynthetic complex I mentioned, that's realistically what happens. But then there are other situations where you might want multiple excitons at once. However, to do that, it causes my Hilbert space to grow a lot. So right now I'm solving everything exactly with the Lindblad master equation, and it's already kind of slow because for an n-site system, I have to do operations with an n squared by n squared matrix. So I'm going to look into using more advanced computational techniques, such as using tensor networks or even some more. I've heard of neural quantum state methods before. I think those have been applied to open quantum systems in the past. Anyway, I'm interested in leveraging more advanced techniques to do calculations with multiple excitons and maybe also higher dimensional systems like lattices instead of just chains. Right, so I'm going to just acknowledge that all this research was done on the traditional unceded territories of Indigenous peoples in Canada, specifically the Huron, Wendat, Seneca, and Mississaugas of the Credit. Also, I'd like to thank Dvira for meeting with me every week to talk about this. Also, Matt back there has done a lot of simulations for me and helped solve a lot of computational problems. Juan Carrasquilla at ETH Zurich and Eric Gauger at Heriot-Watt University have also been advising this project a lot. And Aaron Fung, who I don't think is here, did a lot of analytical work for me, which helped me work out what parameters to use to get interesting results. Right, so yeah, I think I finished 3 minutes early, if anybody has any questions.
Questions, please?
When you have the three-side multiple coupling situation, and there are two solutions, right?
Mm-hmm.
Why the two solutions where the side two moves away, it's not, they move away by a different amount depending if it moves up and down?
Yeah, so I don't have a superb answer to that. And part of that is something we've noticed is that there seems to be with many sites a preference to have negative energies too, even though it should make a difference with infinite temperature. My best explanation I can give you looking at these contour plots is just that with these ridges, there's a lot of possible optima where the gradients are near zero. So I'm specifically using an algorithm called optimistic gradient descent that uses estimates of the second derivative to make sure you don't get stuck in saddle points. I think that what's happening is there's something in that algorithm that ends up calculating that this is the optimum based on its estimates of the second derivatives nearby instead of, say, over here, where this ridge would extend to. Yes.
When you couple the system with the bath, you also, besides the Lindblad terms, you get a change in the H sub S in the energy. The kind of renormalization, so on. Are your energy differences much larger than that, much smaller than that?
Sorry, could you explain again so I couple my system to the bath. My HS energies, though, I fix and are what I'm optimizing.
Usually when you derive
Okay.
derive the Lindblad equation and so on, you get the Lindblad terms, but you also get energy shifts.
So we fix the environmental numbers, so this we count the energies that are optimized.
Right, I was just wondering if those shifts, how those shifts compare the energy differences.
We didn't calculate that, yeah.
We didn't.
Okay. I said look back and say those shifts whether they are actually can be interpreted as part of the energy shift. Yeah, we didn't.
I mean, I'm just worried about the scales, you know, and they're just interested in scales and how they would, yeah.
So you didn't report the value of the environmental noise here?
No, I figured it would be boring for me to just spew a bunch of numbers at everyone. Here my environmental noise is 0.1. So my energies you saw kind of ranged between like orders of 1 or 2. So there's like a factor of 10 difference between my environmental noise and the energy scale for a lot of these results. For the, where is it? Yeah, over here with the short range coupling in many sites, my energy differences are about the same as the environmental noise.
Just wondering what's going on. There's some mix up with those X there.
Based on that, what could means that those energies, your interpretation would be that part of the renormalization of the clearance.
Yeah.
It's not a real shift of energies that one should implement, but already.
Yeah.
It's more the interpretation of what should one think, how should one think about those energies? Come from the environment or really? Yeah.
I have a question about the setup of the problem.
Yeah.
Why are you interested in simplifying the behavioral system at infinite temperature? Like I would say the most quantum thing would be at 0 temperature.
So choose maybe is a strong word. The Lindblad master equation with the local decoherence operators I'm using ends up being equivalent to an infinite temperature limit. You can implement temperature using the Bose-Einstein distribution, but it's more complicated. You have to change bases. So as a starting point, I'm using infinite temperature, knowing that it's probably not the most accurate description, but now that I've completed that, I'm moving towards finite temperature.
And if it's an infinite temperature, how classical it must become sort of classical, right? Is this result just can you just describe as classical like interactions?
Yes, what you mentioned, what should be done is local decoherence, and the expectation is that it is as if the temperature was increased because going up and down with local decoherence. So then it is a quantum effect, which is in terms of temperature. It is as if there is no bias to going up and down. In that sense, it's infinite. It's quantum. Right?
Follow-up question from interesting look. The infinite temperature, usually is that meaning that your lexicons are very localized.
So it depends on this capital gamma, which is the strength of my environmental noise. In my case, they are not that localized because of, I've mentioned briefly that environmental noise assisted quantum transport. The way the environment kind of interacts with the bath, you can almost think of it as the environment is kicking the bath, and every kick, it's like it makes a measurement and causes a collapse, while also introducing an exciton. So if you're not kicking that fast, then you're not really adding that much energy, so you end up with localization. Or if you're kicking really fast, you're constantly collapsing your wave function, so you end up with like the quantum Zeno effect where nothing happens. I chose this gamma specifically because it's often where you would see an act happen, where those two effects kind of cancel out and you end up with enhanced transport. Sorry, does that answer your question?
So, what's that might be small? I think the sort of accepted perspective is noise assisted transport.
It is.
It's the regime more than transport.
Mm-hmm.
Sure that has it in mind.
Yeah.
Gradient of the energy sort of optimized at I just optimized transport. It does seem pretty interesting. There's a pretty big difference between the two regime. But again, I think the chromophore models, they use a lot more sites, so it could also be artifact sites here, so I'm sure the connectivity of that as well as problem.
Yeah, but are you thinking specifically of the SMO complex? Yeah, there's, I think, kind of in my equivalent to what I'm doing, it would be like 7 sites and the coupling is complicated. There's only certain pathways it can take. But yeah, so it would be a more complex version of what I've done here.
Thank you very much.
I assume you can figure this out.
I think, yeah.
Yeah. Yeah.
All right, everyone, thank you for coming. Gonna do a real 180 shift on you from the theoretical work. I'm mostly gonna be talking about pretty much all experimental stuff. Specifically moving to using on-chip nanophotonics, dispersion engineering, hybrid materials like that for both entanglement and quantum squeezing. So I'm going to start off by going through the applications for quantum optics, why we care about this, why we want to go towards on-chip stuff, and stuff like that, and then talk about a little bit, so we're all on the page of the doing quantum optics on chip, and then specifically talk about 2 big projects that we're doing in the Helmi group right now with on-chip polarization and entanglement, and some new stuff that I'm working on as well as involving on-chip squeezing. So the first thing I want to talk about is spectroscopy. So compared to normal spectroscopy, well, 1, it can be bulky. But 2, in this paper, they actually did some that was published in 2012, so quite a while ago now. But the main point is you can actually use entangled photons to access both spatial and temporal modes that are not accessible using classical light. As there's, like hybrid states, as we can see in this. Oh, there's laser pointer. Okay, cool. On the right, where you can use both photons to get to the different states that you might not be able to using classical light. Sensing, you can use it for, so the main application types of sensing are environmental monitoring, on-chip biosensing, where you can place a biological sample on chip in a Max-Zegner interferometer setup where you have a sensing arm and a reference arm. Then you use homodyne detection to detect it. Or you can do magnetic fields as well, as shown on this chip, where you have sort of your nonlinear optics shown on the chip here, where you have a probe, you have your probes, and then your cooling, and you're also and pumps here in this case, and you go through all your optics and stuff, and your sensing is all done here. And then there's also off-chip sensing, where you can, which I'm going to talk about in a couple of slides more specifically, but there's another project we're starting to work on in this group where you sort of use visible or near infrared with microwave RF. They call it optomechanical transduction, where you entangle a visible or near infrared photon with an RF or a microwave photon. You keep that photon on chip, and then the other photon can go through hundreds of kilometers of fiber, and they'll still remain entangled. See quantum computing, which I'm sure everyone knows the most about. However, where you actually have on-chip entangled and squeezing laser sources to go through micro wings, where you generate you can generate your squeeze light and your entangled light as well, and then going through to your sensing optics on the far side here. However, there's a lot of problems with this so far. Obviously, for your single photon detectors, they have to be at really cool temperatures, like we're talking a couple of Kelvin. So, I mean, that's all, you need to do that at a big, large room scale right now. You can't do that. I mean, you can, not really on chip, not yet, but, you know, getting towards that point, you know, like using most promising stuff so far is that sort of semiconductor single nanowires for single photon detection. And then talking about going back to the keeping one photon on chip and one photon off chip, what I was talking about, where you generate your photon pair source and you send it through a polarizing beam splitter. And one goes to measure, you know, detect a target or measure some sort of target, for example, in communications. Then the other stays on chip or stays in fiber. Then you bring them all back together and you do your detection and your data processing. I'm actually, and I don't have any results yet, but I'm started a really cool project on this, basing on using a single ring resonator where I can generate both my microwave or RF photon and my visible or near infrared photon in order to do this, all on chip. And then the main two things I'm going to talk about today are quantum entanglement and quantum squeezing. Obviously, for squeezing, you can have the difference. Yeah, everyone knows most people should know the difference between non-squeeze light and squeeze light, where you can squeeze either your amplitude or your phase for accurate, ultra accurate measurements, when it comes to sensing or computing. And then through quantum entanglement as well, where this is your density spectral function up here. For it, I mean, it's kind of cut off at the top of the, but basically these portions in here, when you have these at a non-zero amplitude, that shows entanglement. And to get a maximum entanglement, we want these as close to 1 as possible. Now, to do all this experimentally through entanglement or through squeezing, we have to use nonlinear optics. So we either have in natural occurring materials, and we either have, you know, sort of a Chi2 or a Chi3 response from material systems, and through quite a variety of parametric processes, such as, you know, spontaneous four-wave mixing for Chi3 or Chi2, you know, difference frequency generation, second harmonic generation, and all that sort of stuff. And then you need pump photons as well, which can be generated off chip or on chip. We've generated them both off chip and on chip in our work that I'm going to be talking about coming up. And then we can also do all this. It actually requires dispersion engineering using different materials, tuning the width and your thicknesses of your waveguides and all your on chip nanophotonic components through critical tailoring to get, you know, your phase matching and your index matching, so you can get access all sorts of different modes and have high tunability in your nonlinear portions of this to generate entangled sources and squeeze sources. I'm going to be talking about specifically for the entanglement today's polarization entanglement. However, you know, there's time bit entanglement, there's frequency time entanglement that are also potentially possible with the things that we are working on. So, as I mostly talked about, starting on the left-hand side here, you know, like we also see an optics lab, you know, it's full of so many lenses and filters and, you know, like big sources, OPOs, all that sort of thing that, you know, are really, really bulky, and, you know, like are meters on scale. So we want to reduce this down to on chip, which has greater stability and reduced demand on resources. And obviously, you know, it's like back when Microsoft had their first started with the computer, you know, it was the size of, you know, a room, right? And look at what we have for chips. It's the size of, I can't even, you know, on my finger, you know, of what we put into our computers. So we want to do the same, but that's for electronics. We want to do the same thing with using photonic devices. So that's sort of what the group principle is, where we want to go from, you know, doing these on a wafer and actually packaging them into chips is what we're focusing on in our group and our work. So there's a couple different material platforms I'm going to talk about with doing this. The first is for entanglement, where we're focused on Chi2 materials, where we have aluminum gallium arsenide, which is highly tunable with for the doping concentrations of your aluminum compared to your arsenic. And you can vary that highly using MOCVD, and you can make like quantum wells doing that by growing these things. and get all sorts of cool structures and actually get on-chip lasing with these as well, which I'm going to talk about in next couple of slides. However, with this, I mean, the only thing is it's tough to integrate with other materials easily. You know, it's like a periodically pulled lithium niobate. Integrating it, you know, on a heterogeneous platform is still quite difficult. And then the other for CQIQC for squeezing I'm talking about is basically a silicon, where it's easier to integrate metals and dielectrics. You know, in foundries they can integrate all sorts of metals and dielectrics on these platforms. However, the one problem with silicon is that the nonlinear loss can be very high, especially at telecom wavelengths, 1550 from 2 photon absorption. So we want to try, we don't want to work at those wavelengths. So anything over the band gap of silicon, which is around 1,000 nanometers, 1 electron volt, is going to be a non-starter for this. So for the entanglement sources, what the structures we've grown, we started with a gallium arsenide substrate, and we've grown through using what we call Bragg stacks based on Bragg's reflection principle, where we start out, we have 4 stacks on the bottom and 4 stacks on the top. And then in the middle, for our core of our waveguide, we have 2 quantum wells surrounded by 3 quantum barriers with different doping concentrations of aluminum gallium arsenide. And what we can do with this is I actually can create a P contact and an N contact and launch a potential difference within the quantum wells that we can get actually lasing out of this. So, and then an SEM of this structure is shown here. And then for the CQIQC different frequency generation or spontaneous parametric down conversion, sorry, too many acronyms. As you can say, we have our, as I talked about, we have our P contact and our N contact. So we can actually generate light from the core, which ends up being at 780 nanometers. Then we inject our signal externally, and then we highly tune this signal. We can actually tune the idler wavelength that we get out, and then these photons end up being entangled through CQIQC, polarization entangled. The effective index has to be phase matched to access these modes through the CQIQC. So we get the access of, we guide through the core using what we call the Bragg mode through the Bragg reflection principle at our 2 omega frequency, or the 780 nanometer wavelength that I talked about. And then through normal conventional TIR is where our signal and idler modes are guided. And then to get the the electric field profile of these modes in the Bragg stack, where in the Bragg core, sorry, of the LGAS structures, where the blue curve is the Bragg mode, or the 780 nanometer wavelength, and the red curve is our TIR wavelength. Here, as they're both guided within the core. And then through our SPD process through our CQIQC, we have 3 different types of polarization entanglement that we can generate. We have type 0, where we have a TM pump, and then as well as the signal and idler TM as well, or P polarized, whatever your convention is. And then we have type 1, where you also have a TM pump, but then you have TE signal and idler, or type 2, where you have a TE pump, and then you can also have a TM and a TE signal idler, or vice versa. Also, what we've done is that we've added photonic crystal, 2-dimensional photonic crystals on each side of the cladding of these structures to get further dispersion control, where we can see that for the Bragg mode, the effective index of our mode hardly ever changes, but compared to when you have a photonic crystal, we can get more tuning of the index to get higher, better phase matching and more efficient SPDC or DFG. The losses do increase a little bit, unfortunately, with this, adding the photonic crystal cladding. However, we still emphasize that because of the dispersion control and the TIR mode shows lower loss, which is the most important point here, because these are our entanglement pairs, and we can just increase the current to overcome the loss from our pump to pump out more light in the Bragg mode. the LGAS devices have very, very high tunability, and they have a bandwidth of 95 nanometers for the TM and the TE modes, which shows that we can get good tunability for our polarization entanglement for both signal and idler modes if we want the degenerate case or we want the non-degenerate cases where signal and idler mode are different wavelengths. And we can tune the injected signal over a wide variety of wavelengths within that bandwidth that we get confinement. And the generated idler is also highly tunable as well. So we can access, overall telecom, SLC, U bands within the telecom range. So, and then we can also have further tuning through, we have temperature controllers and the input current of that we pump into the quantum wells in the LGAS devices to get, if you pump up higher current, you end up getting a red shift of the Bragg mode. So you can have further tunability that way. Here's our experimental setup of how we measured this, where we send our input through and we use lenses to couple into our BRL devices, then a low pass filter to filter out our pump mode. And then we have a multi-mode fiber and an OSA in order to detect and polarize the entanglement. And obviously, we have single photon detectors to detect the polarization entanglement. For the equation for the we're focusing on type 2 SPDC. If you remember, that was where you had a TE pump, and then one of the signals was TM and the other was TE. Where this is the joint entangled state, where this phi is the joint spectral amplitude of each case of the HV and the VH. And to get a maximally entangled state, these need to be equal. So we want those to be as close to each other as possible. And we go through and we look at our experimental results, and through type 2 SPDC, we get a high degree of concurrence and a high fidelity of almost 1 with a very low error, as we can see through our density function here as well. Most of the photons are entangled as well for the real part of the function, and relatively low loss. For type 0 and type 1, it's not as efficient, but we still do get because of the difference in the phase matching, the difference of the spectral bandwidth of the TM compared to the TE modes, and the different Chi2 element for the TM and the TE modes. But we still do get a high degree of concurrence at 0.85 and 0.89. However, the optimal solution with our waveguides is through the TE pump, which the TE modes ends up having higher confinement in the core of the waveguide as well. So this is the ideal case of why we would rather have this than a type 0, a type O, or a type 0 or a type 1 SPDC for phase matching. And then to talk about briefly on-chip squeezing on a silicon platform. In this paper that's was put out by Sir Massey EC or Sir Massey et al. In 2023 last year, focuses on silicon nanostructures, where if we look at the dispersion curve, where the band gap is the white here, and then the radiative mode where so these are silicon, sorry, so start again to make more sense. The blue is a silicon nanostructure on a silicon dioxide cladding, so silicon on SOI cladding. And if we line these up, we can form an array, which ends up being guiding light. And this period is what controls the what sort of regime that we're operating in. So if the period is large, we're going to have nothing but radiative modes, as you can see here in our dispersion diagram. And then the band gap is where we're not allowed to operate. And then SWG is all subwavelength rating, so the light sees it as one homogeneous medium. It doesn't see it as an array of scatterers. So we want to operate in the Huygens regime, where it's you think like going back to your basics optics course, like a Huygens regime where each sequential point acts as a secondary source of light as you propagate along, and these actually end up being resonant. and strongly confine light and keeps on building up the electric field as you move along this this waveguide. And they've formed these into arrays, into waveguides. They've had they've had curves, we've had Y splitters as well, where you can control the amount of light split into each direction by just controlling the distance that these are apart. And you get relatively low loss, like on the order of 0.1 dB, even for bending radiuses as low as 6 to 9 microns, which is very good. And same for the splitting. You get low loss as well for your Y splitter. For a conventional Y splitter, it's comparable compared to where this is full silicon. It's not an array of the scatterers when I say a conventional Y splitter, and versus the Huygens splitter, which is with the array of silicon. So what I've done is I've turned this, excuse me, I've created a 20 micron diameter Huygens ring, as shown here, which has strong confinement and a high Q factor for the loaded case when you have a bus waveguide to couple the light out. When you don't have any waveguides attached to this, you can actually get a Q factor of over 4 million for a ring that's only 20 microns in diameter with this, which is huge, and creates a higher degree of nonlinearity, which will allow for better squeezing. And even still, when you add a waveguide, the Q factor only goes down to almost 500,000. And you can obviously tune the Q factor when you move your bus waveguide up and down and closer to the ring resonator. And 500,000 is still very, very high for a 20 micron ring, where usually you need these rings to be on the order of hundreds of microns to get Q factors that are that high. So the design of this ring is where, to get squeezing, is where through spontaneous four-wave mixing is the nonlinear process that we're going to get our squeezing in this case, where you couple light in using special Huygens coupler, because you need to excite these modes that we've engineered. It's a very specific Huygens mode of the silicon scatterers, the silicon Huygens dielectric scatterers, into the Huygens waveguide, and then that couples into our Huygens ring, where we get our squeezing that we can control, and then we get the squeeze modes through the output ports that are shown here. And this is preliminary work so far. There's still more work to do on this project, but we're in the process of sending it for fabrication and hopefully get back some good measurements and good results too. But earlier simulations, I don't have it up here, but they're showing at least on the order of 2 dB of squeezing, which isn't bad. I mean, for on chip, I mean, considering, I mean, most off chip squeezing, you know, you can get like 10, 15 dB now in like state-of-the-art pipeline sources, but obviously those are big and bulky. And I mean, hopefully we can get better than 2 but I mean, with fabrication and tolerances and stuff like that, it's not going to be easy, but we will see what happens. So to summarize, we were able to generate polarization entanglement on an LGS platform with high fidelity for the type 2 SPDC case. And then through dispersion engineering, we can control the phase matching and get a high tunability for the phase matching and our for what wavelengths we operate at for both degenerate and non-degenerate cases for polarization entanglement. And then for we can get Chi3 squeezing using spontaneous four-wave mixing on silicon using the silicon Huygens nanoscatterers and nanoresonators to create high Q rings for on-chip squeezing. And with that, I will wrap up, and thank you everyone for your time. Be happy to take any questions.
Thanks for the cool talk. So I have a question about some of the entanglement
Yep.
and stuff. So in a slide with your like diagram before that.
This one?
Before the I don't maybe before that one. Yeah, perfect.
Okay.
So maybe I just like completely misinterpreted this, but did you say that you use like the electroluminescence from your like PN junction, that light to pump your
Yes.
SPDC?
These are pumped on chip. Yeah.
But okay, so like how do you did you say you get lasing from them?
Yeah.
Okay. I think that my understanding is that you would I was just surprised that the signal is strong enough to like pump, because I would assume you got like single photon emission from the
So yeah, it acts as, whoops. Need to press the right laser. It acts as, that's like sort of our gain medium, the quantum wells. And we pump it with the current, and obviously that, with the current, and we have to use about 100 milliamps, and we've gone all the way up to 500 milliamps of what we have to pump this with. In order to get, but no, yeah, we do get lasing, as we do get, pair generation out of this, and we get recombination, reverse process, and we get lasing out. And the signal is it has to be weak, but we still do see both DFG and SPDC with these on-chip lasing sources. Anything? Yeah.
Is there a benefit to smaller radius resonators besides like scalability? Like, do you have less loss?
No, usually when you get decrease the size of your resonator, you increase the bending rate, or decrease the bending radius, and you actually end up increasing the loss with this. And but besides scalability, I mean, there isn't. Usually they're lossier for when you have a straight silicon ring compared to, but because these are resonant, these scatters, we end up actually getting a higher Q and higher field at the smaller scale. So that's why we are looking at using these as compared to a conventional silicon. So yeah, besides scalability, I would say, yeah. Anyone else?
So for the temperature and these on-chip devices, how important it is to have them still in well-maintained conditions?
So for the LGAS devices, we actually use we have them on like a temperature truck, so we can tune the temperature, and we use that tuning of the temperature. We can get redshifting of our signal of our idler wavelength, sorry, as well. So the temperature does have it is quite critical to in controlling the signal in idler, because it's very sensitive to that. Absolutely, yeah.
For these on-chip sources, how do you usually separate the signal?
Like separate the signal from the idler. So usually we use beam like I think I have, do I have a diagram on here? It's not in this diagram. No, but we do usually we use a polarizer. Like so usually these will be especially for type 2, you know, like the signal's TM on the idler is TE. So if we just rotate our polarizer, that's how we can separate out what is the what's the signal and what's the idler.
Perfect time, so thank you very much.